Pandas is more than just a way of holding tabular information. Join me today as we learn how to fix the missing values in real-world datasets. Welcome, I'm Gregory Talkwine with GNT Learning. On this episode, I'm going to help you clean up a Pandas data frame. Now, the whole of Pandas is far too much for a single video to describe. Instead, what we're going to focus on today is taking a single data frame, identifying the problems it has, fixing the values where we can, throwing out the values when we can't, and cleaning up some data types along the way. What we won't be discussing in this episode is how to deal with dates, string manipulation, or the conversion of categorical variables. Our overall goal here for this episode is to give you the core set of tools you need to begin working with and tackling real-world data problems. Today we're going to start off with some data regarding South African heart disease. We already have a Jupyter notebook set up where we've imported our most common imports and read in the data file. While a pretty clean data set overall, there are some little issues we need to catch and fix before we can do any modeling. At a glance, we immediately see two issues. The first is this unusual column over here called unnamed 0, and the second is this NaN value in the CA column. Now, the second issue is more of a lucky catch. Generally speaking, if you look at a data frame and just put it to the screen like this, you're not going to see any missing values. If you do, it can be a sign that there's actually quite a few missing values to actually see one directly. But in general, this is not the way to catch these, and so we'll do a little more robust version of that later. First, though, let's handle the issue of what is going on with this unnamed data column. Unnamed data columns are actually fairly common and can come from a number of different sources. To better understand this problem, let's go look at the raw CSV file itself. Here, we have the data for the raw CSV. Now, we don't normally go into looking at a raw CSV file like this. It can be a bit unwieldy to actually visualize and understand all the data. However, we're doing it today just to help elucidate some of the underlying mechanisms of what's going on. So here we can see in this first row where the actual column names are coming from. And we notice that the very first column is an empty string. Because it's an empty string, we end up with this unknown column name when it gets read in. The other very common source we don't have in this file is if the number of columns in the actual header doesn't match the number of columns in one or more of the rows later on. When this happens, the extra information is automatically filled in with NAs for the row values and unknowns for the column headers. Now, not a problem today. The things we're going to do to solve our issue with this particular case will be applicable there as well. So now let's turn back to our actual Jupyter notebook and see if we can fix this value by renaming some columns. All right. So here we're going to take advantage of actually looking at the columns themselves using df columns. When we do this, we get a printed index of columns that shows you what's there. And we can see the raw string for exactly what's being interpreted. Now, one option we have here is if we want to just change multiple column names or do a lot of work, it is sometimes useful to just directly write a new column name and reset all the values. We can do this by simple pasting here and then manually changing whichever names we want. So we could make this, new column number 1. However, this is a little bit of a brute force approach, and we only actually have one column whose name we want to change. So we can do this in a little bit more controlled of a fashion. So we're going to comment this out and not use this as our solution today. Instead, we're going to come down here and use a function called rename. Now, the rename method of a data frame does pretty much exactly as you would expect and allows us to rename one of the columns. In this case, we want to rename that unnamed column. Now here it's a good idea, instead of trying to type out exactly, to grab the name from the columns of what you want to change. In our case here, it's a well-behaved, well-listed name, and we could do it by hand. However, a lot of times you'll have strange characters in terms of extra spaces at the end of column names and other unusual little formatting glitches that aren't super visible in the display itself, but will be written out explicitly in the df.columns output. So in our rename itself, we have to give a dictionary as our input, where the key is the old column name and the value is the new column name. Now, when we run this, we're going to find that nothing really changed. So what went wrong? Well, the rename by itself actually defaults to trying to rename the index of the rows rather than the column names. If we wanted to use it to rename columns, we have to tell it to use the axis of 1. Right? So by default, most things in Pandas data frames default to an axis of 0, which corresponds to rows, as opposed to an axis of 1, which corresponds to column. So if we do this, we see that we can, in fact, create a new column name for our column of interest here. Now, we need to actually save this back into the data frame, and we have two options for doing this. We can either do this relatively directly by saying df equals df.rename and get the new data frame and save it into df, or we can use the in place option. We can say in place equals true. When we use in place equals true and run the code, it changes the data frame in line as it was done, and then if we look at it afterwards, we see that it has the new value. What's important to note here, though, is that we do not want to mix those two methods. If instead we say df equals df.rename and use in place is true at the same time, we're going to get up no result for df. And the reason for this is without the in place equals true, this rename function returns a new data frame. With the in place function equal to true, it returns nothing. So we need to decide if we want to get the result as a return, or if we want to use in place to do it in place. Mixing and matching them will cause you to have a none type object which prints nothing for the output here. Okay. I prefer to not use in place, but that's more of a personal choice, and so you can write whatever piece of code is most comfortable to you. Now, since I have done this already, I have broken the code and erased the df I had originally. So now I need to rerun my code to pull the data back in. So we do kernel, restart and run all, and restart and run all cells. And that'll take just a moment. All right. And now we have our new data frame with our renamed column. Now, let's step back for a second. This is a great way to rename a column, either multiple columns, so we look at it up above, or to rename a single column, as we did here. However, we got a little bit ahead of ourselves, actually, and we just said, oh, here's a column name, let's fix it, what can we do? We didn't actually stop and look at what this column actually was. If we take a moment to look, we'll see that actually, 1, 2, 3, 4, 5, oh, wait, this is just an index column. It's a very common bug you'll run into when writing and reading things from data frame is that by default, when you write things to file, it writes in a column for the value of the index, but doesn't give it a name. And so we turn around and try to read it back from file, it goes ahead and creates an unknown column name with that index. We don't need to doubly define our index here. So what we actually want to do is when we read the file in, we want to read this in as the index column. To do that, we need to step back a little bit and think about how we're reading this from file in the first place. So let's look at how we're actually reading these files in using read.csv. And we can actually use the question mark here as part of the Jupyter Notebook to pull up the documentation for that function. You can find exactly the same documentation online through a simple search. Here, I just want to bring it up for our local viewing. We see there's actually a ton of optional arguments that exist when we do the pd.readcsv. We've been giving it a first optional argument for the file path, or the first argument for a file path, and there's a large number of optional arguments after this. Some of the most important ones to highlight are near the top, which are sep, which allows you to read in things other than a comma-separated values, using some separator other than commas. Of other note is the dtype argument, which we'll talk a little bit more in future. Skip rows, which you can use to deal with the fact that you have maybe some text header above where your actual data is in a data file. And the one we need for our purpose today, which is index call. Index call will allow us to specify which column is to be used as the index when we read it in. In this case, we're going to use index call equals 0. We want the 0th column to be an index column instead when we read it. So let's scroll back up here to our initial reading in of the file and add index underscore call equals 0. And before we rerun this, let's take a quick moment to go ahead and get rid of this code. And now we can do kernel, restart, and run all. Now, when we do this, we actually obviate the need for a fix to our data frame. Now our column of values that was mysteriously labeled is now an index. Importantly, the code we had before to rename the column doesn't throw an error here. There's no column with a given name, it simply moves on without changing anything. So we don't need the code anymore, but I'm going to go ahead and leave it here for reference. Moving on, let's now talk about missing values. First of all, where do they come from? Well, they can come from a lot of places. If we go back to our CSV file, we can see, say, scroll down for a moment, that we have a lot of values in here, including, for example, an NA. And if you look at the values above and below it, you can see that this was a column that had all numerical values but then had an NA value inside of it. So in this case, there was an explicit NA given, and the the Pandas data frame, when reading it in, interpreted this as a missing value for an int. Likewise, if you give it an empty string or a lot of other different characters, it will automatically figure out for you for itself whether or not it should be reading it in as a float value, and then this is a missing column or missing item, or if it should be a string column where there's some numerical looking and some character looking, but all string items. And in general, Jupyter Notebook does a pretty good job of making this automatic choice for us. Seeing that there's this automatic type identification going on for us, let's go ahead and see how the data frame is actually being interpreted in our specific case. To do that, we can use df.info to get a better description of what is going on. Now, in general, I highly recommend using df.info for any time you load in a data frame to see what's happening. In this case, it's highlighting two very important things for us. First of all, if we look at the number of non-null values, we can see that the CA column is actually missing 4 values, and that this THL column, or thou column, is missing 2 values. Additionally, we can also see what data type every single column is being read in as. And as I said, the default choice by the data frame is generally pretty good. However, we can use the dtype option in the read CSV to overwrite this if we want to. The most common case when you want to do something very deep in the work is that you want to overwrite things to be strings so that you can manually edit them and fix how they're being interpreted yourself. Today, we're not going to get into the topic of dealing with strings and really aggressive data correction. We're going to handle the more common case of they're simply missing values. So now that we see where these values came from, where are they exactly in the data frame? What is it that we're missing here? Well, one of the easiest ways to get a little bit better view of what's going on is df.isNA. Now, by itself, it doesn't return the most useful result. It just shows a data frame filled with false and true values for every single data point, telling you whether or not it is something that is being classified as an NA type object. Now, again, our data frame was a large chunk of data, so looking at this directly is not going to be very palatable. Instead, we want to use some additional operations on this, usually the sum operation, which will allow us to see how many NAs there are. And we can do this either by row or by column by using the axis argument. So here, when we say axis equals 0, we're summing over the rows and giving back the columns that correspond to the NAs for counting. We mentioned before that when we say axis equals 0, we're talking about rows, and axis equals 1 equals columns. So when I say axis equals 0 here, why do we get a list of columns? And the reason for that is that the sum operation is not asking for the axis to keep, it's asking for the axis to do the summation over, i.e. we want to sum all of the rows together. So what's left is a collection of columns. And we can see how many rows are missing data for each column. In this case, we see we're missing 4 for CA and 2 for thou. Likewise, we can do it with a value of 1 here, and we can see how many values are missing in each row. It turns out this is actually slightly more useful for our immediate case, even though it's not immediately readable, because what we can do here is use greater than 0 on this and get back a list of true and false values. The reason this is useful is because data frames act like NumPy objects in a lot of ways. And one of the ways in which they do that is that they accept a list of true-false values as an input for access and return the items for which the value is true. That means if I do df open square bracket a list of true and false values of the same length as the data frame, it will return a subset of only those items for which the condition was true. In this case, the condition was has NA values. So we're now able to get a list of exactly which rows are missing data from our data frame. Now, it was a couple steps there to build up this function, but we do have a reusable function here that will give us back the set of rows that have missing values for any data frame. With that in hand, we can now look at our specific data set and begin to ask the question of what are we going to do? In general, there are 2 options when it comes to these missing values. You can either fix them or you can throw something away. In terms of throwing something away, we can do it by row or by column. And in terms of fixing it, we have similar options. What we see here is that we are missing only 6 values out of 303. And so a reasonable choice might be that, well, let's just throw away the missing values. So let's look at that option first. The most direct way to throw away data is df.dropNA. When we run this, we get back a new data frame. And you can see here it has 297 rows as opposed to 303 we had originally. We just threw away the rows that corresponded to missing values. This can be a valid choice when you have a small number of missing values. And like the rename method above, there is an option here to do this in place or by assigning the data frame back to itself if you want to keep this. Okay, so we threw away data by row. What if I wanted to throw it away by column instead? Well, it comes back to our axis argument again. So we could use axis equals 1, and now instead of throwing away the rows that are missing values, we threw away the 2 columns that were missing values. This might make sense if you have one column where there's a huge number of missing values and most of your points are missing that value, that maybe it's the column that's the problem, not the row. This worked reasonably well, but let's get a little bit more precise. Well, maybe I have a mixture of bad columns and bad rows, and I don't want to just throw everything away at once. Well, the easy solution here is to use the subset option. So we can use the subset for one of our column names with missing values, CA. And when we do this, what we're doing is we're throwing it away, again, row-based by default, because we had axis equal to 0, we don't specify it. And it threw away the rows where CA was missing, but it did not throw away the rows where thal was missing. And in this way, we could combine multiple things. So we say this axis equals 0, and then we could go ahead and throw away the columns that are missing data otherwise. So in here, what we've done a combination. We first threw away rows where CA was missing stuff, and then we threw away any columns that were still missing information. So we're saying effectively that, okay, we want that missing values in CA is not a critical problem, just those single points are bad. But any other columns that are missing value, we're not going to try to salvage, we're just going to throw them away. Right? And in this way, you can combine multiple row and or column dropping of NA. So that's the solution if you're throwing things away. What if instead you're trying to fix the data? All right. Well, the most straightforward option there is df.fillNA. Now we have to provide this an option for what to fill with. If we go ahead and just run this, with value 0, we'll see that, okay, we get back a data frame the original size, and if we did a little more inspection here, we could find that we've changed our NA values to 0. That seems like a solution at first glance. Now, obviously, we had 2 different columns here. We had CA and we had thal. Well, putting 0 in for CA might have been a reasonable choice, but for thal, that was definitely not the right choice. If you look at this, we see the actual values possible are fixed, normal, and reversible. More generally, we can get a better view of exactly what values are possible by looking at a specific column and using .unique to see what is available as values. So now I see fixed, normal, reversible, and NaN, because we've not fixed it. All right. So if we want to do a fill NA where we give different values for different columns, we have to use the optional argument value equals, and then we provide a dictionary whose keys are column names and whose values are the values we wish to fill in. For example, we can now say we're going to use normal and 0 as our values to fill in our data frame. Now, at first glance, looking at this table itself, you're not really going to be able to see a difference. And this is why it's important to make sure that you actually know what values you want to fill in. It's very easy to say 0 is some default value. Okay, I'll fill in with that. But is that really the right choice? So for thallium, we wanted to label. Well, what about for CA? Is 0 even the right choice? Sure, it's numerical. There are other zeros. But is that the best option? One way we can investigate this is to investigate the CA column a little bit more. So let's look at df of CA and look at the mean value, for example. So this would be a way of doing mean imputation. Is we find the mean value of a column and then use that as the fill value. So write this here, find out here the value is, and plug it in. Now you'll notice that our column was missing values, had an NA, but we're still able to do this calculation. So a lot of the calculations that Pandas does in terms of mean or standard deviation or whatever actually work with NAs. They simply ignore the NA and don't include them in the mean. So we can use it to do simple imputation type corrections. However, this also means that if you're doing some early analysis of your data frame and looking at means and things like this, you can completely miss that there are NA values if you don't explicitly look for them at the beginning. So it's very, very important that you explicitly look beforehand, because this will not tell you that there are missing values. But let's dig a little bit deeper here. Instead of plugging in a value of 0.6722, what if we actually look a little bit more at what values are available. And we'll see, oh, sure, CA looks like a float value, 1.0, 2.0, 0.0, but really it's more of an integer. So a value of 0.76 would probably be a pretty bad choice for an NA fill. And in general, I don't know this data set incredibly well. I can't tell you what these numbers actually mean. So it's probably not a good idea for me to make a blind choice about the best fill NA. I could use the most common integer in here by using mode to get that value, but that doesn't really tell me if that's the best choice. Instead, I need to have some deeper understanding of the actual system before I can start doing fill NA in a meaningful fashion. So again, mode was in this case was the most common, so 0 may be a good choice. But without understanding the system, I shouldn't make that decision. You'll see a lot of times people give rules of thumb for how to fill in NA values, and there's a lot of code online that makes some reasonable assumptions, but they're just that, they're reasonable assumptions. They're not an actual understanding of the code, or rather, an understanding of the data. You need to make sure you understand your specific data set and what values make sense for it. In general, the default you should tend towards is just not to include data that is broken or missing values. The risk there is that if for some reason you are systematically have NAs for a particular type of data, that throwing away the NAs could cause a bias to the problem. Now, once you've made a choice between what it is you wish to fill and what you wish to drop, you can now combine these options together. Right? So let's look at combining some options. Let's say after doing our background research and analysis, I decide that the best choice here is to drop the values, i.e. in the rows, where the CA value is missing, but to just fill in the missing thou values with normal. Right? So to can do that, I can simply call my multiple options and string the different methods together. Here I'm going to do subset equals CA, and then I'll do dot fill NA with normal. Now notice here when I'm doing that fill NA normal, the only column left is thou, so it's okay to just use fill NA directly like this. And in doing so, I'll create a data frame, and perhaps if I like it, I can say df equals this. Right. Now, before I do this though, I should make two really key points. One, I am meaningfully changing the data here. I am throwing away rows. I am changing values. So saying df equals df or using the in-place operator are both somewhat questionable here. You're creating a risk that when you go back and change something earlier, you're going to end up with misaligned data, and if you get off going back and forth, you can create some real confusion for yourself. So it's really good when you're going to make a meaningful change from your original data to your post-cleanup data that you go ahead and have a variable name change at this point. Now, this is definitely a matter of preference and flow control in the end. I prefer to put a df clean here after I do all my dropping and filling. To be perfectly honest, it'd be better to have some function to kind of wrap this away to the side to help provide an even better level of separation. But for a simple one-liner here, this is sufficient. All right. Now, the last thing we're going to touch on today is we're going to go a little bit further in talking about data types. So as I mentioned before, Pandas does a pretty good job by default of figuring out what to do. Well, let's say it just got something wrong. So if you remember, we saw that for our CA, that we get our values, and it's by default putting them into floats. And this is not quite what we want. So we can use the .asType method to turn this into an integer. But we got an error. What happened? If we go and scroll down, we'll see cannot convert non-infinite values NA or inf to integer. We're not using our clean data. So this will be one of the many, many ways in which your data can break. So instead here, let's use our now cleaned data to try to convert. All right, so we see we are able to successfully convert this into an integer. And now though, if we want to put it back into the data frame, we need to go ahead and clean, specify the column that we want to set. In this way, we've converted C8 to an integer and then assigned it back to the same column to overwrite the original data. Likewise, we could also do something like convert this to a string or any other data type that we might need. In this case, I'm not going to save it back to the original data frame because I don't actually want this as a string. I was very happy with it as an integer. All right, so putting our code back. So with that, we finished our main evaluation of basic cleanup of data, fixing data types, finding NAs, filling NAs, dropping NAs, and talked a little bit about reading in files from CSV as well. Now, one question that might come up is, well, what about how does this thing behave when there's NAs in it? For example, we showed that when we had the mean here earlier, that it still worked even though there was NA values. And there can be a lot of little distinctions about how it behaves if true, false, and greater than, less than, and all these other questions around how do NAs behave. And the short answer is you don't want to know. You don't want to have data that is messed up and that you need to understand those nuances. You want to clean up your data as soon as possible, as early in the process as possible, so you can avoid all the issues that come up with the nuances and corner cases there. Now you can, if you have a specific issue, figure out the details, try it out with a small sample set, and you can get through what you need. But the main thing is you just don't want to have NAs. The most common error, by far, when people have a model they're running and they're trying to get something to work and it's getting some weird, ridiculous, infinite error or NA errors, is that the underlying data has a subtle NA issue that is being glossed over because things like .mean aren't complaining about it. So you need to actively go out and look for NAs when you have data at the beginning, rather than rely on having errors to catch them later. Because the errors you do get from them can sometimes occur much further downstream than where the actual problem is. And the sooner in your process you catch the error, the less time it will take you to find and fix. So save yourself a lot of time and a lot of energy by looking for your NA values at the beginning. Hopefully that will go a long way to alleviating your challenges and making you just a little bit better at modeling. Thanks for watching, and a special thanks to those whose donations help fund and sustain creating content like this. As always, the code produced today is available on GitHub through a link in the description. Remember to like, subscribe, push all the buttons, click all the things, and I'll see you next time.